Welcome to the second module of Power System Operation e-learning course under Mission Karmayogi initiative. Please note, this course uses narration, so remember to turn on your speakers or headphones while taking the course. You can also view the course transcript by clicking the Notes button above. Click Start button to proceed further. Electricity is nothing but the flow of electrons. Electricity flow is similar to the flow of water. Potential difference or voltage difference is required for current flow. Ohm's law explains the relationship between voltage, current, and resistance in the flow of electricity. Depending on direction of current, electrical systems can be AC or DC system. AC system can be single phase, two phases or even of three phases depending on number of phases in the system. Power grid systems carry out the complete process of delivery of electricity to its consumers starting from its generation to high voltage transmission then to distribution till it reaches the end consumer. In this course, we will learn the basics of the power system and understand the various stages of the electric power grid. After going through this module, you will be able to explain the basics of electricity and associated laws, understand the difference between direct current or DC and alternating current or AC, outline the process of how a power grid works, understand the importance of balance between power load and power generation and how it is maintained, and identify the obligations and schedule to be maintained in a control area. Electricity is briefly defined as the flow of electric charge, but there is so much behind that simple statement. If we look deeper, electrons are negatively charged particles, and they always flow in the opposite direction of current. The force required to make current flow through a conductor is called potential difference, which is measured in voltage. For example, the first element has more positive charges, so it has higher potential. On the other hand, the second element has more negative charges, so it has lower potential. The difference between 2 points is called the potential difference. Now, let's see how the flow of electricity is similar to the water flow. Potential difference between two nodes determines current flow, and water flow is determined by pressure between 2 points. However, both flow from high to low only. While flowing through a water channel or pipe, water encounters resistance similar to conductor resistance in the case of electricity. The flow is inversely proportional to the resistance of the path, that is, the more the resistance, the less the flow. Resistance is inversely proportional to cross-section of water channel and conductor. More the cross-section, less the resistance. Now, we shall learn the fundamental law of electricity. Ohm's law explains how voltage, current, and resistance are correlated. According to the law, the voltage difference will be equal to current flow multiplied by the resistance of the circuit when voltage difference, current flow, and resistance are measured in volt, ampere, and ohm. We know that when current flows through the circuit, it has to work against the resistance, which further develops heat. Heat dissipated through the conductor is equal to I square R, where I is the current flow through the circuit and R is the resistance. Joule's law is a mathematical description of the rate at which resistance in a circuit converts electric energy into heat energy. It states that the rate of production of heat by a constant direct current is directly proportional to the resistance of the circuit and to the square of the current. If voltage of transmission line is increased, less current is required for transmitting same amount of power. So, heating loss reduces with increase in voltage level of transmission line. Electricity comes into forms alternating current or AC and direct current or DC. Both are essential to enable the functioning of our electronics.
What are the major differences between them? And do we use both?
There is a big story behind these forms of current and their usage. In 1880s, an epic battle started between Thomas Edison and Nikola Tesla. Thomas Edison and his company supplied power with the help of DC technology. Nikola Tesla and George Westinghouse started to use AC for transmission of power. AC has one inherent advantage. In case of AC, voltage can be stepped up and down very easily with the help of transformer. We have already learnt that heating loss reduces with increase in voltage level of transmission system. Gradually AC became popular in spite of DC having head start. Let's understand the major differences between AC and DC and know which one is preferred over the other. In direct current, the current only flows in one direction, whereas in AC, it changes direction periodically. The frequency in a DC system is always zero. In case of AC system, frequency varies within band across nominal frequency. Nominal frequency is different for different frequency. Like India and European electric grid follows 50 Hz system, while USA follows 60 Hz system. Though AC won the initial battle, but it had stability issues in case of long-distance power transmission. Even sending AC power through cable encounters large amount of loss after some distances. In such cases, DC was proved to be more economical. With the passage of time and better knowledge of the advantages of both forms, the world has opted to use both AC and DC. Let's check your understanding. Drag and drop each term towards its correct formula. Let's check your understanding. Select the correct option. Have you ever noticed a physician checking your pulse?
Yes, sir. Once I had fever. The doctor checked my pulse and confirmed the same.
Correct. And are you aware of the pulse of electric grid?
Does current also have pulse?
No, it's not like what you are thinking. Frequency is the pulse of any electric grid and voltage at the node is the blood pressure. Let's see why. Frequency refers to the number of times the current switches between positive and negative in 1 second. The unit of frequency is Hertz. For example, if a current changes between positive and negative 60 times a second, we say that it has a frequency of 60 Hz. Frequency is the indicator of load generation balance in the grid. When generation in the system is more than load, frequency shoots up and reverse occurs when generation becomes less. To cope up with these modulations, generation at other running generators are increased or load is reduced. For this reason, system operator continuous monitoring of grid frequency. Their target is to keep frequency always within IEGC band, which is now 49.90 Hz to 50.05 Hz. Similarly, voltage describes the pressure that pushes electricity. The amount of voltage is indicated by a unit known as the volt or V, and higher voltages cause more electricity to flow to an electronic device. When reactive power consumption increases at any particular node, voltage will reduce and vice versa. Operators are to take action to increase reactive power injection or reduce reactive power consumption at that node. Reverse action to be taken when voltage increases at any node. It is important to maintain any node voltage within IEGC band, which is 728 to 800 kV for 765 kV voltage, 380 to 420 kV for 400 kV voltage system. Frequency is monitored for whole grid, but voltage is monitored for each node or bus separately. Hope you are now aware of the pulse and BP of electricity.
Yes, sir.
Let's understand the types of AC circuits. There are various types of AC circuits, such as an AC circuit containing only resistor, an AC circuit containing only capacitors, and an AC circuit containing only inductors. Click on each type to know more. An actual circuit is a combination of all the three. Like various types of circuit, there are various types of power also.
Are they also of two types?
Yes. The AC power is mainly classified into two types. They are active power and reactive power. The portion of power that is absorbed and used by the load is known as the active power. It is always positive. It does not change its direction. Reactive power, sometimes called wattless power, is the power consumed in an AC circuit that does not perform any useful work but has a big effect on the phase shift between the voltage and current waveforms. Apparent power is a combination of active and reactive power. In an AC circuit, the product of the RMS voltage and the RMS current is called apparent power. This is all about the types of power and their importance.
How do we use the AC system of current?
It has phases and is used according to the requirements. Let us now learn the types of AC systems. Single-phase system is the simplest electrical circuit. It requires only two lines, one for power to go in and the other is a return path for current. These are often called line 1 and line 2 or line 1 and neutral. Current only has one path to travel in a single-phase circuit, such as a control circuit. Three-phase systems are bit more complex. They use three current-carrying conductors, called line 1, line 2, and line 3, which have a 120 degrees phase shift in the and waveforms between them. Each of these conductors are connected to a three-phase load, like a three-phase motor. Click No More to learn the key differences. As we know, a three-phase system uses different lines and conductors to carry current. Let's learn in detail about the types of connections. The three-phase systems are connected in two ways, that is, the star connection and the delta connection. In star connection, the starting or finishing ends, similar ends, of three coils are connected together to form the neutral point. A common wire is taken out from the neutral point, which is called neutral. It is also called Y connection. In delta connection, the opposite ends of three coils are connected together. Let's check your understanding. Drag and drop each type in the respective box. Let's check your understanding. Select the correct option. I will show you the power grid system using an image. But first let's know what the system means. The electrical grid is the intricate system designed to provide electricity all the way from its generation to the customers. These systems have grown from small local designs to stretching thousands of kilometers and connecting millions of homes and businesses today. Now, with the help of the image, let's see how the entire system works. Power generating stations are located at feasible places according to the availability of the fuel, the dam site or an efficient location for renewable sources. This is very practical since the transmission of electrical power over longer distances is a lot much economical than the relative transmission of any other fuel. Also, a hydroelectric plant must be located according to an appropriate dam site, or a wind power plant may be located offshore to harvest additional energy from the wind. Thus, a long-distance transmission system is needed to transmit the generated electricity to the populated areas. And a distribution system is required. Law of conservation of energy states that energy can neither be created nor be destroyed, it can only be transformed from one form to another form. Electricity is generally produced by converting mechanical energy into electrical energy, that is, electromechanical conversion systems. In the majority of cases, the mechanical energy is either obtained from thermal energy or provided by the flowing water. The main sources of thermal energy are coal, natural gas, nuclear fuel and oil. Hydropower is the main non-thermal source of mechanical energy used in electricity generation. Electricity is generated in power plants, which are often located far away from the populated areas. There are various types of power generating stations such as thermal, nuclear, hydro, solar, wind, etc. Electricity is generated in power plants at voltages ranging from 11 kV up to 25 kV. Generation voltage cannot be much higher due to technical limitations. Let's understand how power is generated from water. Large-scale hydroelectricity projects typically involve dams. Runoff river and tidal projects also harness the power of moving water to generate renewable electricity. A hydroelectric dam converts the potential energy stored in a water reservoir behind a dam to mechanical energy. Mechanical energy is also known as kinetic energy. As the water flows down through the dam, its kinetic energy is used to turn a turbine. The generator converts the turbine's mechanical energy into electricity. This electric energy then goes through various transmission processes before it reaches you. Transmission and distribution are the methods to transfer electricity. The transmission power lines are for long-distance, high-voltage electricity transportation, whereas distribution power lines are for shorter distances and lower-voltage electricity transportation. To illustrate, transmission lines are the power lines you might see on the side of the freeway, while distribution lines can be seen on the sides of streets. Furthermore, we shall look at the differences between the two. Transmission. Carry electricity over long distances, that is, across the state. Transport bulk electricity at higher voltages, typically between 60 kV and 800 kV. Usually supported by tall metal towers. Electricity travels in both directions. Uses a three-phase supply system. Distribution. Carry electricity over shorter distances, that is, to neighborhoods and communities. Usually supported by wooden poles, at a lower height than the metal towers used for transmission lines. Electricity is carried in one direction only. Uses a single-phase supply system. High voltage transmission. High voltage means low current. Power loss due to heating is small. Electric power transmission network should be efficiently used. To reduce power losses. To reduce power transmission cost. To improve the efficiency of power transmission. An overhead line consists of conductors and ground wires, towers, insulation, hardware, and foundations. The transmission line conductors are specialized, with large cross-sections and relatively few strands. Normal AC power lines use phase conductors with a central core of a few steel wires, surrounded by a sheath of many more aluminum wires wound in helices of alternating direction. Click each part to learn the importance. Earth wire. If the earth wire is not present, direct lightning on the phase conductors will travel to both sides, damaging the end equipment, and will result in a power outage. The earth wire is usually grounded, earthed at the top of the supporting structure to minimize the likelihood of direct lightning strikes to the phase conductors. Reduces voltage stress along the insulator string during lightning stroke. Cross arms hold the insulator to the tower structure. Insulators support the conductors and withstand both the normal operating voltage and surges due to switching and lightning. They are used according to the voltage level. High voltage conductors, used to carry electrical power from generating or power stations to a distribution substation. Aluminum conductor steel reinforced cable ACSR is a type of high-capacity, high-strength stranded conductor typically used in overhead power lines. Transmission towers are structures built to support the high-voltage conductors of overhead power lines. Based on numbers of circuits carried by a transmission tower, it can be classified as single circuit tower, double circuit tower, multi-circuit tower. Let's see the basic differences between them. Single circuit transmission line refers to an arrangement of conductor over the transmission tower. In single circuit transmission line, three conductors corresponding to three distinct phases, that is, R, Y and B phase, are run on the transmission tower. Double circuit transmission line refers to the arrangement in which a total of 6 conductors are provided to make two different transmission circuit. In double circuit transmission line, there are two circuits each consisting of 3 conductors corresponding to 3 phases. Multi-circuit transmission lines have multiple circuits connected to the same pylon. They are able to transfer more power over a particular distance. The towers significantly reduce the aggregate row requirement of transmission lines. An overhead line consists of conductors and ground wires, towers, insulation, hardware, and foundations. The transmission line conductors are specialized, with large cross-sections and relatively few strands. Normal AC power lines use phase conductors with a central core of a few steel wires, surrounded by a sheath of many more aluminum wires wound in helices of alternating direction. Click each part to learn the importance. Based on numbers of circuits.
Sir, is transmission done only through overhead wires?
No, like telephone lines, they are transmitted underground also. Now, you will learn about it. Underground transmission lines are electrical or telecommunications cables that are installed beneath the ground. At present, there are two types of underground power transmission cables which are assembled in a pipe and solid dielectric cable. Underground cables essentially consist of a conductor, an insulating system, a wire screen and a sheath. At the core is an electric conductor. In the case of extra high voltage EHV lines, this is usually made of copper. The conductor is enclosed by an insulating system, dielectric, whose main component is made of plastic, for example. An outer copper wire screen discharges the fault currents and keeps the electric field in the cable. The outer cable sheath protects the cable against moisture. Now that we have understood the two types of transmission, let's analyze the differences between the two and know which one is the most preferred. Click each feature to learn the differences. Based on the differences, the underground cables are found to be more expensive to construct and install. However, they are beneficial in areas where overhead wires cannot be constructed. The overhead cables are preferred more due to their economic nature and ability to carry more power. Let us now see how. Let's explore the high voltage direct current or HVDC electric power transmission system. HVDC transmission is widely recognized as being advantageous for long-distance bulk power delivery, asynchronous interconnection, where two different regions operating at different frequency is to be connected, and long submarine cable crossing. HVDC transmission system is the combination of AC and DC system. First, the generated AC voltage is converted into DC at the transmission end. When it reaches the receiving end, DC is inverted to AC for distribution purposes. So, in order to carry out this operating, we need conversion devices at both ends of the transmission line. Let us now see how HVDC and HVAC differ from each other. Overall cost comparison of AC and DC transmission. The power is transmitted between terminal stations that convert the voltage levels. So the total cost of transmission depends on the terminal station's cost and the cost of the transmission line plus losses involved in it. We will look each one by one. First one is terminal station. The high voltages are transmitted between electrical terminal stations and their job is the voltage conversion. In the case of AC, the equipment used for voltage conversion at these terminals is mainly transformers that convert between high and low voltage. While in the case of DC, the terminal stations use thyristor or IGBTs-based converters for conversion between high and low DC voltage. Since the transformers are more reliable and cheaper than these solid-state converters, AC terminal stations are cheaper than DC terminal station. Therefore, voltage conversion in DC is expensive than AC. The transmission line cost depends on the number of conductors being used and the cost of the transmission tower. In the case of conductors being used for transmission, the HVDC transmission requires only two conductors, while the HVAC transmission system requires 3 or more than 3 conductors. Losses increases in HVAC system as distance increases. If we combine above all three parameters, for cost comparison we arrive at a break-even point which is 600 to 700 km below which AC transmission is cheaper and above that DC transmission system is cheaper. HVDC are also used for connecting to different grids or regions which are having different frequencies, so that variation of frequency disturbance of one area cannot travel to other area. In this, DC transmission is not involved. Purpose is to only connect to different regions. Bhermara to Bahrampur HVDC back-to-back, which is India-Bangladesh interconnection with 1000 megawatts capacity. India is currently having these HVDC networks. Capacity additions in pre-existing HVDC networks are also driving the overhead transmission network in India. For instance, during 2019 to 2020, deployment of HVDC substations is witnessed in multiple projects, including Jharsuguda SS with capacity addition of 3000 megavolt ampere, Aligarh 765 kilovolt GIS, and others. In total, the nation increased the capacity of the pre-existing substation by the 1 to 870 megavolt ampere, with the HVDC-based substations holding a significant share. Amid this, Power Grid's 320 kV 2000 megawatt Pugalur, Thrissur HVDC project was inaugurated on 19 February 2021. The project, with cost of 5,070 crore rupees, is part of the Raigad Pugalur Thrissur 6000 megawatt HVDC system and enables the transfer of 2000 megawatt to Kerala through the HVDC station at Thrissur. Earlier in September 2020, Power Grid Corporation of India Limited commissioned Pole 1 of the Raigad Pugalur HVDC transmission system comprising Raigad HVDC Terminal Station, Chhattisgarh, and Pugalur HVDC Terminal Station. Let's check your understanding. Select all that apply. Let's check your understanding. Select all that apply. Let's understand the importance of load generation balance. Electricity presently cannot be stored on a large scale due to economic and technological constraints. When demand is higher than generation, frequency drops, and when generation is higher than demand, frequency rises. Changes in demand throughout the day and over the seasons are met by controlling generation or by controlling demand in some cases. System operator strives to maintain the load generation balance in order to maintain the frequency within the narrow band normal specified band under IEGC. Now, we will see how it is important in maintaining balance between load and generation. Different frequency bands are shown in the graph. Frequency dip and rise in frequency shows load generation mismatch. As shown in the graph, frequency is below the normal band. It indicates load is much larger than generation. Similarly, for rise in frequency above the normal band, generation available is much higher than the load. Now, we shall see how the frequency is controlled by the generators for maintaining balance. This figure shows the frequency control at 4 points. At the frequency sample point, the output frequency of the generator is monitored. At the comparator, the output frequency is compared to the target and a frequency error is determined. The speed controller calculates the necessary adjustments to correct the frequency error and make the actual frequency equal the scheduled frequency. Finally, the speed controller adjusts a valve position to allow more or less working fluid, such as steam, water, gas, etc., into the generator. Let us now learn the power system states. Click each state to learn more. A system is said to be in normal if both load and operating constraints are satisfied. Load generation is balance, all grid parameters within normal range, so system is in normal state. System moved from alert to emergency with further tripping or large disturbance with cascaded tripping, causing more deviation of frequency and other grid parameters. With help of emergency controls, the system can be again brought back to normal state directly if possible, or else to alert state and then to normal. Emergency controls are mentioned below. System protection scheme. Load trimming scheme. Generation reduction scheme. The system will return to the normal or alert state by means of corrective actions, disconnection of faulted section or load sharing. Some contingency occurring, such as tripping of generators, load, lines, etc., causing frequency and other parameter variation beyond normal band. This has brought system into alert state. Preventive controls for bringing system to normal state from alert state. Primary, secondary, AGC, and tertiary control. Load generation redispatch. Manual load shading and generation revival. System moved from alert to emergency with further tripping or large disturbance with cascaded tripping, causing more deviation of frequency and other grid parameters. With help of emergency controls, the system can be again brought back to normal state directly if possible, or else to alert state and then to normal. Emergency controls are mentioned below. System protection scheme. Load trimming scheme. Generation reduction scheme. The system will return to the normal or alert state by means of corrective actions, disconnection of faulted section or load sharing. When the system is in emergency, if no proper corrective action is taken in time, then it goes to either emergency state or extremis state. So emergency control action is done to bring back the system state either to the emergency state or normal state. Apart from this, also under extremes, the defense mechanism should be there to not have complete blackout and various parts of system could be split and saved. Ultimate objective is to not reach the in extremis state of operation. Each level having its own defense mechanism for returning back to previous state. From this state, the system may be brought back either to alert state or secure state. Hence, in certain cases, first the system is brought back to alert state and then to the secure state. Moving forward, Let's understand inertia and its importance in the power system. Inertia is the resistance of any physical object to a change in its velocity. This includes changes to the object's speed or direction of motion. The kinetic energy stored in these spinning parts is our system inertia. If there is a sudden change in system frequency, these parts will carry on spinning even if the generator itself has lost power and slow down that change, what we call the rate of change of frequency, while our control room restores balance. Grid inertia is a form of energy storage which addresses imbalances between supply and demand on electricity grids over very short time periods, typically on the order of fractions of a second to several of seconds. In the grid, it gives the system operator a chance to respond to power plant failures, called contingencies. This is because inertia resists changes in frequency, giving other systems time to respond. Although it cannot be sustained for more than a few seconds, it provides time for the mechanical systems in the grid to detect the imbalance, as reflected in declining frequency, and tell power plants to speed up or slow down. Let us now quickly learn the benefits of interconnected systems. Swapping peak loads. The peak load of the power station can be shared by other stations connected to it. Reusing older plant. Obsolete or older plants can be used during loads for a short time. Economical operation. Less efficient plants operate only during peak loads, hence making it cost-effective. Diversity factor. The demand on a particular system is reduced as the load is shared. Reduced plant reserve capacity. When several power stations are connected in parallel, the reserve capacity of the system is much reduced. This increases the efficiency of the system. Reliability of supply. In case of major breakdown in one station, continuity of supply can be maintained by other healthy stations. Now, we will learn about the obligations and schedule of a control area. A control area is a combination of systems to which a common generation control scheme is applied. This is connected to other systems of electrical networks by transmission lines, called tie lines. First, let's have an overview of the obligations. The main objective of power system operation and control is to maintain continuous supply of power with an acceptable quality to all the consumers in the system. The system will be in equilibrium when there is a balance between the power demand and the power generated. Now, let's understand scheduled and unscheduled interchange. The export schedule of a control area through tie lines is scheduled interchange. As per current methodology adopted, 24 hours of a day is divided into 96 blocks of 15 minutes each. Each control area manages its portfolio of its own generation, share allocation from ISGS, bilateral contracts or purchase through open market to meet its demand in each block. The drawl export schedule of a control area through tie lines is scheduled interchange. Unscheduled interchange is nothing but any deviation from the scheduled interchange. It can be calculated as the difference between actual interchange and scheduled interchange. Here we go with our final topic, the ACE.
What does that mean? Is it related to the control system?
Yes, ACE stands for Area Control Error. It is the difference between scheduled and actual within a control area on the power grid, taking frequency bias into account. So ACE is how much a control area is to contribute to bring frequency to nominal frequency, 50 Hz. Now, We can see how frequency correction is actually done. This ACE signal is used as an input for AGC for a control area to balance the load generation of control area so as to maintain the frequency. ACE is also used as an input for automatic generation control or AGC, which ensures the contribution of the control area towards frequency correction. Interconnection frequency is sensed and its deviation from scheduled frequency, 50 Hz, is calculated and this frequency error along with UI is fed to AGC module. AGC output accordingly gives signal to control area generators to increase or decrease generation to maintain frequency at scheduled frequency. Let's check your understanding. Arrange the states of the power grid system in the correct order. Let's check your understanding. Select the correct option. You have reached the end of this module. I hope you must have understood the power system fundamentals.
Yes, sir. It was a great learning experience.
Let us quickly summarize the major takeaways of the module. Electricity is briefly defined as the flow of electric charge. Electrons are negatively charged particles, and they always flow in the opposite direction of current. Electricity comes in two forms, alternating current or AC and direct current or DC. Both are essential to enable the functioning of our electronics. There are various types of AC circuits, such as an AC circuit containing only resistor, an AC circuit containing only capacitors, and an AC circuit containing only inductors. Electricity is generated in power plants, which are often located far away from the populated areas. There are various types of power generating stations, such as thermal, nuclear, hydro, solar, wind, etc. HVDC transmission system is the combination of AC and DC system. A control area is a combination of systems to which a common generation control scheme is applied. HVAC has a higher line cost than DC for the same transmission capacity, as it requires at least 3 conductors while DC systems only requires 2. Electricity and the laws associated to it. Understood how direct current DC and alternating current AC are different from each other. Learned the basics of an AC system and explored the types of an AC system. Learned the entire process of how a power grid works from generation to transmission and to distribution. Compared transmission lines like HVDC and HVAC transmission. Understood the importance of balance between power load and power generation and how it is maintained. Learned about control area and how frequency management is necessary to maintain equilibrium.